So what we're going to start talking about today is actually combined units 4 and 5. Because of the lack of Fridays this semester, we only had 14 Fridays this semester. We're going to combine these units just to save some testing time. So your next test will be our last day of class. It will not be cumulative. That next test will only be on these last units. And that's going to be that May 11th, I believe, is what that ends up being. Yes. So we have 2 more weeks of lecture after today, basically. So let's go ahead and jump into that material. And the material we're going to be covering, actually both units 4 and 5 are beyond what you would need to get through the program here at WITC if you're in the 2-year ADN or medical assistant or paramedics. But for many of you, you are going to have to, especially ADN now, the laws are changing to where most likely you're going to end up having to get a 4-year degree at some point in your career. So this is kind of that prep for going into a 4-year degree. Most bachelor's degrees will require a college algebra or at least a college intermediate algebra and a statistics class. And that's what we're going to be starting on in these next probably 5 hours of lectures. We're going to be looking at those topics. So today we're going to start talking about representing numbers and relationships. You may have seen the representation of a number on a number line. And all that number line is, of course, from 0, you go in both directions. Positive numbers go to the right. Negative numbers go to the left. And when I teach arithmetic, adding, subtracting, and especially working with our integers, negative numbers, I always use the number line for it. And there are 2 ways to represent a number on this number line. For example, the number 4 can be represented with what's called a vector. A vector is just an arrow that starts at 0 and goes to that number. Like that would be the number 4 there, represented by a vector. Negative 4 would then be the same length, just the opposite direction. Pretend I had the scale right and those are the same length. And this can be used for adding numbers, subtracting numbers, dealing with negatives, and all that. Well, that's more of a working definition or a mechanical definition. If I just want to represent the value 4, I can just put a dot on that number line at 4, and that represents that value. If I'm not looking to do operations, to do any sort of calculating with the numbers, but I do want to represent several numbers, that's the simplest way to do it, is to put a dot at that location. Well, oftentimes in application, we have a need to show 2 numbers and they're related to each other. An example might be, height and weight. We might have that a patient is, let's put down 71 inches in height and a weight of 165 pounds. Well, we need to show that there's a relationship between those. Those are the same person. We just took 2 different measurements off of them. And this happens a lot in math and representing data. What we did here is called an ordered pair. It is a pair of numbers, and the order is because the order does matter. In this case, that first number is always the height, and the second number is always the weight. We might have another patient, that is 68 inches tall and 149 pounds. Again, the first number is the height, second number is the weight. And we can have several of these ordered pairs, one for each patient or each member of our sample that we draw information from. So how would we represent pairs of numbers like this graphically, like we did with these values on the number line? Because looking at this set of values is kind of, I mean, it gives us exact numbers, but doesn't give us a picture of how those numbers set. Well, normally I'd go through a whole development of this, but because of our lack of time, I'm going to jump right into it. About 3,000 years ago, a guy by the name of Rene Descartes came up with a solution. And what Descartes' solution was, is if we're going to represent two numbers, we need two number lines. And the way Descartes set it up was, we're going to take the first number line, just like we always do, with 0 in there, and then numbering positive to the right, negative to the left. And then the second number line is going to start at the 0 of this number line. And instead of going horizontally, it goes vertically. So that the two zeros overlap each other. And the second number line goes positive going up and negative going down. So this is called the Cartesian coordinate system, or sometimes just called simply the rectangular coordinate system. So to represent an ordered pair on here, let's say we're obviously our 68 and 149 are a little bigger than what's on here. So let's just take a reasonable number like 4 and 7 to represent those two numbers go together. Well, first, that first number in the ordered pair is called the independent variable. The horizontal axis is called the independent axis. Now, many of us have probably heard that referred to as the x-axis. That's because that is typically the x variable is used to represent that independent value. The second number in this pair is usually referred to as the dependent variable. So the vertical axis is referred to as the dependent axis. Again, many of you probably have often heard that referred to as simply the y-axis, because the y variable is typically what's used to represent that value. Let's talk just a touch about those terms, independent and dependent. A lot of people mistake them for causation. The independent variable does not cause the value of the dependent variable, but it affects it. For changing the independent variable would cause us to expect a change in the dependent variable, but not necessarily the other way around. So here, when we did this one up here, why did height come first? Well, if a person gets taller, would we expect them to get heavier? Yeah. As a person grows and becomes taller, we do typically expect their weight to increase. But if a person's weight increases, do we expect them to get taller? Not necessarily. I haven't grown an inch and my weight's gone up quite a bit in the last 20 years. So that one is not true. So changing the height, we would not expect, or changing the weight, we would not expect that to change the height. But the other way around, changing the height, we would expect that to change the weight, affect the weight. So that's why they're independent and dependent. So let's look at plotting that point for 7. So 4 goes on the independent axis, like we said. That's right here is where the 4 is. 7 goes on the dependent axis. Right here is where the 7 is, positive 7. Now we don't plot them at that location. We have to show both numbers at the same time with a single point. My words kind of got in the way here, but it would go right there. That point there, if we followed it down, its shadow falls on the 4 on that horizontal or independent axis. If we followed it over, its shadow falls on that 7. So that is the point 4, 7. This is what is referred to as the first quadrant. Quadrant because you can see these axes divide the surface of the paper into 4 sections. 4 quads, so quadrants is what we refer to them as. This is the first quadrant because both values are positive in that area. And typically in nature, that's what we're working with, is values that are positive. Now, quite often this independent variable becomes time. Anytime that time is involved in something, 99% it's on that independent axis. So we go backwards in time to put us into the negative side over here of that horizontal axis. So this over here is referred to as the second quadrant. There's 2 reasons for that. That's the second most likely quadrant to be used. Also, if you get into trigonometry, looking at the unit circle, that's the direction that the angles go as we go around the unit circle, is counterclockwise. So then we just keep going counterclockwise. Third quadrant down here. And then the fourth quadrant over here. Now, when we're dealing with real data, like I said, we tend to pretty much stay in that first quadrant with all positive values. If I want to plot the coordinate 5, -2, which quadrant is that going to be in? The fourth is going to be over here. So the x value is at 5, the y value is at -2, that point's going to be right in there. How about if I give you a point right there? What's the coordinate of that point? -6 and 4, yes. Remember that horizontal axis or independent axis has to be named first, then the vertical axis, the dependent axis. How about a point right here? It's on the axis, so what does that mean? There we go, that's 0, -3. Anytime there's a point on one of the axes, that means one of those coordinates has to be 0. This vertical axis, the dependent axis, is where our x value or independent value is 0. The horizontal axis, that's where the y value or dependent value is always 0. So this point over here would be 6, 0. Very good. It's 6 on the independent axis, but it doesn't go up or down, so it's 0 for the y-axis. Now again, normally I would spend a little more time practicing plotting those points, but there's some practice in the homework you can have. I want to get to the next stage. Why are we so concerned about putting these points on there? Well, there are 2 things that we're concerned about, 2 reasons why we're concerned about it. One is data modeling. Now, again, most of the time, as we said, data, real life data is going to fall just in that first quadrant where things are positive. And we might, let's say, just to get a decent set of data here, we're going to look at hours studied and percent score on an admissions test. Now, one of the things when making these graphs that you have to be careful of is you have to be careful that the data will fit on the graph. The highest percent score you can get is 100, so this vertical axis has to go up to at least 100. Now, we don't know, there is no like limit on how many hours someone can study. We're going to say that for the people we're looking at, nobody studied more than 6 hours. Now, again, here, looking at that independent versus dependent, would you expect studying more hours to change your score? Yes. But would you expect scoring higher to make you study more? Not really, no. The effect, again, I don't want to use the term causation, but the effect link goes the other direction. Studying more should affect your score, but your score doesn't necessarily affect how much you're going to study. So let's just take a sample of students here. Let's say we have one student who studied for 3 hours and scored 70. So here's 3, here's 70. So that student's going to be right about there. We have a student who studied 5 hours and scored 80. So 5 and 80. A student who studied 4 hours and scored an 85. 85 and 4. Might have a student who studied for an hour and scored a 60. Might have another student who studied for 2 hours and scored 55. Might have another student who studied for 4 hours and scored a 70. So you can see we have points across the graph here. They do not form a perfect shape, but the idea of putting points on a graph like this is to try to come up with a trend. And typically it's a line, but not always a line. Sometimes there are other mathematical shapes it can take on. But for the most part, in most basic statistics course, we look at lines. So is there a line, or do these points approximately represent a line or linear relationship? Well, if I look at it, if I drew a line through them like that, would we say that does an okay job of representing those points? Yeah, we probably could. Now, if we had more points on there, it would be a lot easier to tell if that was a good line or not. The points don't have to lie exactly on the line, they just should be close to it. You might talk about how strongly linear that is, or how weakly linear that is. You might have things like, now I'm just going to throw random points on here. If I put a line through those, does you think that line sort of represents those points? Yeah, it doesn't do a terrible job. Not necessarily as good as the one we just did up there. These points here, would you say that line does a better or worse job than this one over here did? Probably better because the points seem to be closer to it. Well, the points really are the thing, but saying can those points be summarized by a line is really the question that's being asked. Now here, if I draw a line through them, how would you say better or worse? Way worse than either of those. In fact, really don't know whether that line does a good job or if a line like this does a better job. Kind of a range of different lines that would be about the same. That one is hard to describe with just a single line, so it has a weaker relationship. Not all of them are going to slope up like that, by the way. They might look something like this. In that case, the line would slant down across the graph. That's called a negative relationship. Up here, these were all positive relationships. We'll actually talk about this a little bit more next week about direct and indirect or direct and inverse relationships. And that positive relationship, as the independent value gets larger, the dependent value also gets larger. In that negative relationship, as that independent value gets larger, the dependent value gets smaller, or tends to get smaller at least. In the medical fields, that application is probably the most useful. As far as studying data, looking at trends, doing drug testing, analyzing trends over time, things like that. That's a very useful application. The next application actually does have a lot of applications in medicine, but not quite as practical as the other, is if we look at equations like this. Let's say we have 8 is equal to 3x plus 2. A couple of units ago, we solved equations like that. How did we solve that equation? Subtract the 2. So 6 equals 3x, then we divide it by 3, exactly. We got 2 equals x. But what if I have 17 equals 3x plus 2? Is that the same equation? No, not really. There's a different number in there. But when I go to solve it, what do I notice? When we go to solve it, we're going to subtract 2. And again, divide by 3. Even though we got a different solution, x equals 5 or 5 equals x in this case, it was the same steps to solve that equation. In fact, there's an infinite number of equations like that that would take the same steps. I might have 23 equals 3x plus 2. I'm going to solve that by subtracting 2 and dividing by 3 to get 7 equals x. These are what's called a family of equations. They all have an identical, in this case it's the right side, but one side of the equation is identical with just different values on the other side. The steps to solve it are exactly the same. Again, they have different solutions. That family of equations can be represented like this, with having, instead of putting that first number in there, just putting y in there. And what that's saying is, no matter what value we put in here for y, we can solve it, and we can have a value for x, and we would solve it by subtracting 2 and dividing by 3. And that would give us an infinite number of sets of solutions. For example, up here, in this one, y was 8. So x was 2, made y 8. Here, when x turned out to be 5, the y value was 17. Here, when x turned out to be 7, the y value was 23. So that's telling us when we put it in like this, as y equals 3x plus 2, what we're saying is we can put in any value for x, and there will be a value for y there that makes that a true equation. So up here, we represented a few of the possible solutions to that equation. How many solutions are there? There's infinitely many, isn't there? We can pick absolutely any number we want for x. Or in fact, we can pick absolutely any number we want for y, and we can solve it to find the value for the other variable. So trying to list them out like that would not be adequate. We would miss several solutions. So the easiest way, at least the most accepted way in math, I should say, is to represent that on a graph. that line right there, or that equation, y equals 3x plus 2, is going to look like this on a graph. It actually forms a line. Well, how did we get that line? We're going to look at some shortcuts in a little bit, but the initial method, the first method we would use to graph an equation, in fact, we'd use it to graph any equation, would be to make a table. And in that table, what we're going to do is kind of like what I showed you up here. We're just going to pick values for one of the variables and then calculate what the other one has to be. Now, the way this equation is set up, what would be simpler? Would it be simpler to put a number in for y and then solve to find x? Or would it be simpler to put a number in for x and then calculate what y has to be? Probably be simpler to put numbers in for x. Because if I put a number in there for x, I just have to do my order of operations to calculate y, don't I? So that's what we're going to do. We're going to make a table where we're going to pick values for x, then we're going to calculate what y has to be. Now I want to put points that kind of scatter across my graph. So let's put x equals -2. If x equals -2, what that's saying is up here, that variable x gets replaced with -2. So y would equal 3 times x becomes 3 times -2 plus 2. What's 3 times -2? -6. -6 plus 2? -4. So when x is -2, y is -4. When we look over here, that was a point on our graph. Right there. X is -2, y is -4. Let's try x is 0. I always like to use that one because it's kind of an easy one. If x is 0, y has to be 3 times 0 plus 2. What's 3 times 0? 0 was 0 plus 2. 2. So when x was 0, y is 2. X is 0, y is 2. That's that point right there. Well, to keep these spaced out, let's try x is +2. If x is +2, y would be 3 times 2 plus 2. What's 3 times 2? 6. What's 6 plus 2? 8. So when x was 2, y was 8. So over here, x is 2, y is 8 would be somewhere up here, still on that line. And there's all sorts of other points we could have chosen, but we can see that this forms a line, so we can draw our line through those points. So what does that line really represent? Well, that line is all the solutions to that equation. I can pick any point on that line. Let's say I pick the point right here. That point, I'm going to change color. That point, if I follow it down, x equals 0.5 or 1/2, and y equals 3.5 or 3.5. If I put those numbers into this equation, put 1/2 in where the x is and 3.5 in where y is, it is true. It makes that equation true. Every point on that line, if I find its x coordinate and y coordinate, will be a solution to that equation. I might find -1.2 here for x. If x is -1.2, I follow that over for y, follow it straight down, I would get y looks like -1.6. If I put those in here, that would make that equation true. Now here, because it was a line, I did 3 points and I was able to see that a straight line goes through those 3 points. But there are other shapes that we will get other than a nice perfect line. So how would we handle graphing those? Let's say we have something like y equals x squared plus, Let's see what I want to do here. Plus 2x minus 3. Now I get asked all the time, when I make my table, how do I know what values to choose for x, what numbers to choose for x? Now the answer is kind of unsatisfying, and realistically I don't. I've done enough of these that I have an idea of what numbers, what values work best. So I should use those, I know what values I would like to choose, but realistically, any number for x is going to work, and then we use those to adjust. So let's try the same type of values we used up above. Let's try -2 for x. Let's see what y has to be. So if x is -2, everywhere I see x up here in this equation, I have to replace it with -2. So y would be, instead of x squared, it's going to be -2 squared. Plus, instead of 2 times x, it'll be 2 times -2 minus 3. Now we have to be very careful here. On your calculator, when you do -2 squared, it might try to tell you it's -4 like mine just did. What did I do wrong there? There you go. That -2 has to go in parentheses because it's an order of operations issue. To the calculator, a power happens before a negative does. So if you put it in as just -2 squared like I did up top here, it squares the 2 and then puts the negative on it. Putting the parentheses around it like I did here tells the calculator that's a -2 first, and then you square it. Anything squared should always be a positive, by the way. So -2 squared is +4. 2 times -2 is -4 minus 3. Well, 4 plus -4 is 0 minus 3, -3. So when x is -2, y is -3. X is -2, y is -3 is right there. There's a point on our graph. Let's try 0 for x. If x is 0, y is going to be 0 squared plus 2 times 0 minus 3. What is 0 squared? Careful. 0. Remember 0, you're thinking the power of 0 would be 1. 0 squared is just 0. 2 times 0? 0. Minus 3, of course, 0 plus 0 minus 3 is -3. So when x is 0, y is -3. So 0, -3. Can I draw in a flat line across there? Not necessarily, right? It looks like it's flat so far, but let's try another point just to be sure. Let's try x equals 2. So if x is 2, y is going to be 2 squared plus 2 times 2 minus 3. What is 2 squared? 4 plus, what's 2 times 2? 4, and then we have the minus 3. What's 4 plus 4? 8 minus 3? 5. So when x was 2, y is 5. So here's 2 and 5. Looks to be right there. It's obviously not a flat line. It's obviously not a straight line because those 3 points do not line up, do they? So this is going to be some other shape. But having these first few points on the graph now tells us where we need to find values. Looking at this, I'd like to know what happens here between these 2 points. What value of x would tell us that? -1, right? If x equals -1, that would be somewhere down here between those 2 points, or up here, wherever it is. And we need to know what's going on over here, like x equals -3 or x equals -4, one of those values. So let's try those values and see what we get for y. You guys see what I'm doing? I've got these points, these 3 points on the graph already, and I'm using them to decide what values for x I want to use to fill in points in between them to figure out the rest of that shape, the rest of that graph. So let's try that x equals -1 here. If x is -1, y is -1 squared plus 2 times -1 minus 3. What is -1 squared? 1. What's 2 times -1? -2, and then we have minus 3. 1 plus -2? -1. -1 minus 3 is -4. So when x is -1, y is -4. So -1, -4, it's down there. Well, that helps. That fills in some of our missing pieces. Now we said we needed something over here somewhere. So either x is -3 or x is -4. Let's stay close. Let's use x is -3. Now, I don't know that -3 for x is going to be the best value. Maybe -4 would have been better. At this point, we're trying values to see what it gives us on the graph and seeing what more we need. So if x is -3, y would be -3 squared plus 2 times -3 minus 3. What is -3 squared? 9. 2 times -3? -6. And then we have the minus 3. 9 plus -6? 3 minus 3 is 0. So when x is -3, y is 0. So -3, 0 is right there. So we're starting to get the picture here. We might want to go and put, we may want to put, -1 in for x to see what happens here. We may even want to put, +1 in for x and see what happens here. And we may want to put -4 in for x and see what happens over there. And get those points. If we did that, we would get a point here and a point here. Now it's pretty obvious what shape our graph is. We can draw a curve through those points looking like that. Now that shape there is actually called a parabola. We aren't going to get into too much for parabolas in this class. If you went on to a college algebra or intermediate algebra class, you would do a lot of work with graphing parabolas and that type of equation. For us, any equation like this, we're just going to do what we did here with the graph. Pick values for x, calculate y, and plot those points. And keep plotting points until we can figure out what shape that graph is. So now, I've only done 2 graphs here. Just so you guys know, if you go into Blackboard, I posted for you, let's see if I can make this open. I posted a worksheet for you on graphing equations like that, graphing situations like that. I'll show it to you real quick. Where I give you several equations, and then I give you a table with some suggested values. So in Blackboard, under course information, you scroll all the way to the bottom, there's a graphing worksheet. Now you'll notice I also put the solutions in there. So you could consider this homework, but it's not something you have to submit because I'm giving you all the answers to look at it. But if you look at that, you can see it has several equations. And then you can see I gave you y equals 3x minus 2. Then I gave you a table where I suggested values you might want to try for x and calculate y and plot those points. These may not be enough points. You may need to try others. Or it might be more points than you need. You might be able to figure out what it looks like without having to do all of them. Those are just suggestions to get you started if you're stumped. Over here, you'll notice these points are very different. There's a good reason for that. There are 10 of those. It would be wonderful practice if you could graph those. Again, the solutions are posted there so you can look at them and see how you're doing. That is the first strategy for graphing any sort of equation. Beyond that, there are shortcuts. Those shortcuts are for if we know what shape that is going to form on the graph. Now for this class, the only known shape we're going to deal with is a line. The parabola, if you were going, like I said, if you're going on to a college algebra class, that parabola would be a known shape you would work with. For us, anything other than lines, we're going to make that table and graph it. But for lines, we are going to take a look at shortcuts. The first step is, how do I identify that that's going to be a line? How can we look at an equation and know it's going to be a line? Well, I'm going to give you some examples here of equations that are lines and equations that are not lines. Y equals 3/4 x plus 1 would be a line. Y equals 5 minus 2x would be a line. 5x plus 3y equals 9 would be a line. Y equals negative 1/3 x minus 4 would be a line. Not a line? Y equals x squared minus 5. That would not be a line. Y equals 2x to the third plus 3 would not be a line. Y equals 3x squared minus 5x plus 2 would not be a line. Y equals 12 divided by x would not be a line. Now, similar to that, y equals 5 over x. 5 over x is the same as 5 divided by x. Would not be a line. Y equals 7 to the power of x would not be a line. So if I look at these, can I identify some differences between those equations? More specifically, are there things that appear in these nonlinear equations that don't appear in the ones that do form lines? Yeah. The obvious one is in the first three there, x squared, x to the third. Another version of that might look like this. A square root. A square root is actually a form of a power. So the first thing that we're noticing there is a power on a variable. If I have y equals 2x plus 3 to the fourth, is that going to be a line? It is. There's a power, but is that power on the variable? No, it's not. 3 to the fourth power is just 81. That's the same as saying y equals 2x plus 81. So that is okay. That would be a line. What's the next thing we notice over here? Probably in those two equations. Dividing by the variable, or a variable in the denominator. If we divide by a variable, the equation will not form a line on the graph. So if I give you y equals x over 3, is that going to form a line? Are we dividing by the variable? No, we're dividing by 3. That'll still be a line. It's if it were 5 over x or 3 over x, it would not be a line. Then the last thing, what's going on in this last equation here? Yeah, the variable is in the exponent. Or in the power. Those three things will make an equation be non-linear. So if I have y equals 5 squared times x minus 2, will that be a line? There's a squared there. Is it on the variable? No. That will be a line. Y equals 7x divided by 3. Will that be a line? Yes, we did not divide by x. We divided by 3. That is still a line. Yes. Y equals 5 plus 2 divided by x. No, not a variable. Y equals 8 plus x squared. No. Y equals 1 minus 3 to the power of x. No. So the next step is, once we can recognize whether an equation is a line or not, is to take shortcuts to graph that. And that's where we will pick up next week, is shortcuts for graphing lines. For right now, have you guys look at in the book, page 205. There's only 3 questions there, so 1 through 3. Page 213 through 217. Questions 1 through 15, the odd. And again, it's not assigned. You don't have to do it, but there is a worksheet I posted on Blackboard if you want to practice, filling in tables and trying to graph equations that way. So next week we'll pick up more with these graphing lines, and we'll hopefully finish up all of our graphing. Now, if you guys can, over the next couple of weeks, we only have 2 more weeks of lecture left. I would like to start lecturing at like 8:15, 8:10 if we can. So if you guys can make it in early, that would be wonderful. At the very least, any homework questions and stuff I'd like to have answered before 8:30 so we can jump right into material. But we'll see. Hopefully everybody can get here early. If it's pretty thin, we'll wait. But we're going to try to start a little early the next couple weeks just to finish things up.